So welcome to the second part. We now will do signature with El-Jamal. Okay, so how does it work? Now remember El-Jamal is that we have now a different situation. So we have a prime number. Oh, that doesn't work. So we have a prime number which is known to everybody, which is very nice. So you don't have to create these prime numbers over and over again, like in RSA, where only one knows the prime number. And it also means that somebody else could have generated for you. So the generator is also public, and the only thing you have to generate is the secret, which is just a number, and the public key is g to the x. And the idea is that it's hard to compute x from g to the x, and g to the x is if the secret is taken uniformly from z star p minus 1, then no, z star from 1 to p minus 2, then the public key is also uniformly distributed, so it has no structure at all. Now, so first of all, how does the signature, so how does the encryption work? So just to recall how we do the encryption. The idea of encryption was that we have some random number r, which should be secret, and we send g to the r, and then we have some public key y, and we send y to the r times the message. So that was the signature, and y was something like g to the x. So that was the signature. So it was the encryption scheme. And just to recall, because now the signing scheme is much more complex somehow. So first is you take a random number again, and you compute a g to the k, similar as which is, I just took the naming convention from the book of Delfs and Knebel. So we we have some randomization automatically built in. We compute r, and then we compute when we assign a message, which is m. So we're signing message m, signing message m. We compute r times the secret. So, and we subtract the message from that. And then finally, we have the other secret and compute the inverse of it and multiply it with that. And this is done modulo, I hope that this is correct, p minus 1. I will check it later on whether it's correct or not. And you have to compute a model for that. Okay, so now we have three components. We're sending m, which is the message. We're sending here this is like the public key, a secret k. K must be kept secret afterwards. And we have this s. These are three components, which is not a surprise because we already had in El-Jamal crypto codes, instead of two messages, we send one message, one cipher code, we send two parts. Here we send instead message and signature, we also send two parts. But operation seems to be more complex. So for verification, we have to check whether it's correct. So we get this at the verification side. We only have a public key. So now this is strange here. So how can we compute g to the k? V is equal g to the k mod there's something wrong here going on. So because so v is the same as, I think I broke the scheme here somehow. I should have corrected it somehow. Okay, let's see. So what we do is, so we are giving these three components. So we take y to the power of r. So y to the power of r gives us, so we have y to the power of r, and we multiply this with r to the power of s, r to the power of s. And that's why we're using modulo p minus 1, because now what we do is we're working in the exponent. And the exponent, everything is done modulo phi of n, and this here is phi of p. Okay, so that's the thing what we want to check. So what we do now is we plug in, so to check whether this is the same thing as, so this is something wrong here, because there's a w. Somehow I messed up a slide very, very, very worse, very badly, and but let's see whether I can fix it on run. So let's just plug it in, what we get. So r is g to the k, so this is the same as, so this here is g to the x, so we have g to the x to the power of, and g to the x, which is y to the power of r, which is, strangely enough, g to the k. Okay. And we multiply this with r. R is also g to the k. And we have g to the k. No, r to the s. Sorry, so r is g to the k. And so the exponent is k to the minus 1 times m minus r times x. Okay, so that's happening in the exponent. Now in the exponent, so that's why we have k to the minus 1. Now in the exponent we have k, we are computing modulo p minus 1, so this is really the fitting one. So here we get g to the m minus r times x. Okay, so that's the right component. So on the left component we have g to the x times r, so this was r, so this g to the x times r. So what we get is, after that, if we multiply, we can add it in the exponent, we get g to the m. Oh, we don't get anything because it's broken. So we get g to the m modulo p. Okay, and now I can fix the slides, because if I do this operation here with w, I have to check whether this is the same as this one. And I already have these Mickey Mouse gloves. So that means at this point, this line is wrong. This should be v is equal to g to the m mod p. So that's the thing that we should get out of this. Okay, so then we can check whether this is the same, and it's the same if we plugged in the formula correctly. Okay, would you guessed it? Probably not. Sorry for the mistakes. So again, so I have to change this here into v is the same as g to the m mod p. Okay, so and then we can check it, and this works. Now, interesting here is the following thing: is that a lot of things happen in the exponent here. So compared to El-Jamal, so this was the encryption of El-Jamal here. It is basically only happening, the show is happening below it. But here we use the exponent to do some operation and do some signing, which is a completely new approach to using this El-Jamal, that we use as an exponent. This is something that we use later on, even more, because later on we will use polynomials in the exponent of that, and we use this in order to make the knowledge proofs faster. So, but that's a first glimpse of what is happening here, and this is a widely used signature scheme. Okay, so still El-Jamal is accidentally forgeable in a way which I won't show here. Maybe we do this in the exercise with a corrected version and see whether this is still produce new one. The reason is that, yeah, the problem is that it's still semi-homomorphic and we can produce new things just by using the fact that that if you multiply two messages here, you get to the ciphertext, you get a new one. Okay. Now, how about elliptic curves? Okay. So, elliptic curve sounds cool unless you have to do it. Now, the interesting thing about elliptic curves is, again, that everything is known. So you have A known, you have B known, you actually have this field known, you have a starting number Q, a starting point Q known, and what we need here is we need a publicly known large prime number where we know that n plus 1 times Q is equal to Q, and this immediately implies, because it's an abelian group, that n times Q is the neutral element, and the neutral element is not 0, but it's this strange thing which is the same as infinity. Yeah. So that's something that we need to know. Well, we don't have to find it out because there are a lot of these extension fields published which do this, and the good thing is, like in El-Jamal, we don't need to create one, we just use one, and so we have some secret dA for Alice and some public key PA, which is just dA with A missing multiplied with Q. Okay. Now what we do here so this is a very publicly used signature scheme, is something very strange in such a way, because it seems to combine things which do not belong to each other. So while El-Jamal here is actually working in the exponent, and this everything is going modulo p minus 1, so we actually have a very good overview what's going on. What we do here is, in elliptic curves, we start with a random integer k, and we compute, and remember that all these diagrams that we have is, we have this strange curves and so on here, and you have some x and some y coordinate. Yeah, so this is for real numbers and for the other one, it was somehow complicated. Maybe remember that you have some kind of dots here, and you still have x and y here. Now, what we do here is we look at the coordinate system of that. And we just take one coordinate, which is x. Now, what does it mean? Nobody knows. So you take a random integer and you produce a point here somehow. And then for the digital signature, you just take one coordinate, and we have no grasp what it means. So it's like a random bit generator. And, we know that there are two y's and so on, but these are structures that basically are not used later on. What they use is the following, is that now we take this output and compute modulo n. Now, n is the thing that we need in order to the size, how often do you have to multiply at q until you get to q again. And you have a different function which looks like that. So this seems particularly very close to the thing that we have done here. So this here. You look at the elliptic curves. No, sorry, not this one. This must be the same. So where's the L-Jamal signature? Here, this one. So you can see that is k to the minus 1 m minus rx. And here it's okay, it's not minus, it's plus. That's just this minor thing. But again, we are using k to the minus 1 m times rd. So it's using the same idea. Okay. And so now we send this. Of course, we also send m. So m is missing, plus m. This is the signature that we send. Again, we have three parts, m, r, and s. Okay. So how do we compute the inverse? So how can we check that this is the correct thing? So first thing we have to do is we have to check whether r is inside the scope, because there's a tag if it isn't. And when we compute v, which is, and now we are not using yet the elliptic curves. We're just using the modulo n. We compute the inverse of S modulo n, and that's why we would like to have this as a large prime number. When we compute W1, which is this times the inverse of S, and W2, which is this one, and then we have a first time where we actually use the elliptic curves and compute a point R, where we have W1 times Q plus W2 times PA. Okay. Is there an easy way to explain what's going on? I don't know. But at least we can try to understand why we would check correct signatures. Okay, so why would we correct signatures? So, yeah. So first of all, what we do is we are checking at the end whether XR is equal to R. So we take the x coordinate of R and combine it to the x coordinate of the other one. Again, we compute something and we hope it's the same and only look at the x coordinate. The idea here is that this is a simple function of this point. So we are not, basically we are throwing away the y coordinate. And the check here is whether R is the same as some other number that you just have here and thrown away, which is k times q. So basically this check should be equivalent to is R equal to k times q. Yeah. And we use the x coordinate just as an indicator that we end up at the same point as k times q. Okay, so that's the idea. So we want to check whether k times q is a thing, whether k times q here is the same as R. Okay, so the first thing that we do is, of course, okay, we know that v is equal to s to the minus 1. So s to the minus 1. And this formula here is, so here what we're looking at is this is somehow k times these values, but we want to be sure. So we take the first part, which is W1, and the second part, so this is the signed key. So this is the signature, which is called, what's the name of that? It's, I think, it's M times, no, this is not V, it's just too many letters. Okay, so here I'm computing R, and I'm saying that R is equal to k times q. So I'm looking at what is this, and I call this k, and this is W plus W2, and here by construction this is s to the minus 1 times m plus R times dA. Okay, so that's the division that I have here. So I get W1 plus W dA, which is the same as, by this definition, k times q, because I just plugged in the value on the other side. since s to the minus 1 is k times s is defined like that. Okay, so if you plug it in, we get these values, which are now the same as W1 modulo n. And since the same, we can say this is a multiple of n. If you look at these values, it's a multiple of n. And since we know that this is 0, we can get rid of it and we get r by just plugging in. So that's basically producing the same result. Notice that we just ignored the y-coordinate. It's not used anymore. It's ignored because we want to have a shorter output. And if you know the x-coordinate, then there are only 2 possibilities for y-coordinate. So actually you're not giving a lot of information for that. Okay, so that's the correctness. So again, for security, it's publicly used. It's not clear how secure this is and how well it behaves, but it's a scheme which uses the smaller keys from elliptic curves and makes it more secure. And this is all embedded. And before we go to different topics, I need to mention that this is all embedded into some kind of public key management techniques where you can talk a lot of things about. Because now you can do the following: you don't have to interact with people anymore, but you can leave signatures, which show that something belongs to you. And this idea is to have certificates, which consist of your name, your public key, and the name of a certification authority and serial numbers and so on. And the idea is that if you use public key cryptography, how do we know that it's you? So that's a certain value. So, which is an existential question in German philosophy, which has been resolved by the passport. Yeah. So who are you? I'm the person in my passport. At least that's, if you go to the borderline and it's a border and want to enter another country, and they ask you, who are you? That's an interesting follow-up question. Am I my thoughts, or am I my desires, or am I the future? Am I the potential, what I can do, or am I my past? I think we are coming into deep correction. And officer of border will look at you and stare at you in this moment and say, passport, please. Yeah. And it's not able to engage in this philosophical debate, which probably end up being tasered at the end if you continue like that. Which is, I think, a solution to solipsism, pain. That's okay. You don't know what solipsism is, this is good, don't go there. Okay, so who are you? Or there's this famous article in the internet, nobody knows that you are a dog. Because you could be anything. So the solution for this is authorities. And so if you look at your passport, you will find your name. You find the name of a certification authority. You find a serial number. And you will also find a validity period. What you don't find in your passport, for reasons I do not really understand, is your public key, Yeah. So this would be the perfect place to display your public key according to some cryptographic scheme. Why, why don't we do this? I don't know. Maybe because not enough people are in cryptography lectures. So the public key. And now we have the public key assigned to this one. And what we else do not have is, in your passport, is a signature of your local office, which signs your passport, this is really valid and signed by us. That's also not here. So that this should be signed by the certification authority. Again, this is not there. We made sure that the passports can be read by some electronic device, and probably there's also some signature here, but there's no public key. So if it can be read by some authority, then it will be signed electronically with a digital signature. And what happens is that the certification authority verifies the authenticity of your public key and binds it to some name, and then you get this certificate and you can show it. How do you get your public key certified? Now, you're a student and you want to have it certified. Where? Who? So when I was teaching this some years ago, this lecturer, the university was an authority. The university itself, you go to the computer center and you could have signed it, or you just visit the web pages, and then you can have your public key certified by the University of Freiburg. Yeah, so that's one way to do it. Other way is that the state is already also signing your public key, so it's possible to do that. So then you have your public key and you can actually send messages, and everybody will trust you that this is the case, unless who trusts the university, Are the degrees that you're trying to earn here honest, or is this just something fake like the Trump University? Yeah, which, by the way, existed for some time, if you call that existence. So a fake scheme to actually lure some students to pay a lot of money and give them fake degrees which have no meaning at all. Yeah, which raises the question: isn't every degree some kind of fake? Because the knowledge that you acquired is tested by somebody else who at some point just had a teacher in the history who said, "I'm a teacher," the first one, and wasn't taught by anybody. Interesting point. However, we don't care, since the certification authority has its own public key and will be certified by the next one, and so on. And then we have these always certified chains where we can prove that these are public keys, and we can take this. And this is very easy because you can verify the identity of each other just by showing your certificates and show that it's valid. From some time to time, you will find that the university webpage is insecure because somebody forgot to renew the certification of a webpage. And this is one way to see it. So, what is the infuriating of this thing? The infuriating is that we are spending the energy consumption of some small countries in order to compute some work of proof for blockchain, which can be easily done by a certificate structure. So basically, we're ruining the planet for technology which was 20 years older than the blockchain. And you still find students who will explain to you that this is still necessary. But for the money that they are blowing out, they can send somebody with a plane to this position and say, "I will certify that you are this person and you have this public and private key pair. And we don't need any proof of work for everything that you're doing here because you will sign in this message and send it to public. You don't need this proof of work." That is the most infuriating of this technology because it's just a single slide and just application of digital signatures. And but I have to live with that piece of information, and I have to live with the many students who explain to me why blockchain is still the future and I should invest into it. Which will close the chapter of digital signatures, and we continue to do something which is even more exciting in digital signatures, which are cryptographic protocols. I think since we have some knowledge for how the number tree works, basic level, we can build more than just encrypting and decrypting. And a very nice way to do more is with the Diffie-Hellman key exchange scheme, which has the following goal. So we know that it's very expensive to do public key cryptography if you compare it with symmetric key. You know, AES and DES and whatever are designed in such a way that the operations are very easy for processors because they're bit operations and substitution tables and so on. But public key gives us the possibility to actually send a message to anybody. Now, Diffie-Hellman key exchange is something that takes the one single task of that you want to share a secret key with somebody else, which you could do by just doing encrypting parts of a secret key and sending to and getting the answer into some protocol, which is much easier. And this is the whole protocol. So what we do is we have a large prime number, and we have a generator, and this is publicly known to everybody. So the idea is I want to build a secret, which the only thing I need to know is that all eavesdroppers cannot learn from a communication what is a secret. And the other thing is that I agree on the same secret with the other party. So what I do is, what Alice does is it chooses a random number and sends G to the A modulo P, which is something we know from El-Jamal and the discrete logarithmic assumption, which is secure. So A is completely secure. So A sends this to B, and B does the same thing with a different number and sends it here. Now what they both do, they take the result out of this calculation and compute the power to the A. So they get here K is equal to G to the AB modulo P, which is the secret key. So this is the secret key. Now, so this communication can be completely public. There's no need to keep a secret because the eavesdropper actually knows two things, which knows G to the A and knows G to the B. Okay, in order to calculate G to the AB, the eavesdropper must somehow either know B or A. Yeah, so it's not possible to compute G to the AB and you divide it by G to the B. And because what you get here is G, you can do that, but you get G to the AB minus B. Yeah, so that's not working. Yeah, so this is a very important observation. And Diffie-Hellman key exchange is secure if a discrete logarithm assumption is true. So if eavesdropper can compute that, then eavesdropper can reliably compute discrete logarithms. Now let's do the same thing with elliptic curves. Oh, it's even smaller than this one. So elliptic curves must be something easy. So we take, again, we take some extension field. We don't need any assumptions from the extension field. And we take a random number, and we have also this point. So we compute A times Q and send this to the other person. So we get, here we have PA, and here we send PB. And then we compute B times PA, which is B times A times Q, which is AB times Q. Again, this here is just integers multiplied. So this is, well, it's not happening really because we are just multiplying the point, and it's not a multiplication, it's a strange operation that we defined over the strange plus operation. And here we do the same thing. So we have A times, and when you have brackets, B times Q, which is this PB, and we get the same. A times B times Q. Again, you can see that elliptic curves are in principle the same thing as El-Jamal. That's several way. It's same idea. The only thing is that we have strange operations and smaller key size. Okay, so this is the starting point. Now the next thing we will do is a technique which is called a zero knowledge proof, is that you prove that you know something without showing it. And we already had these ideas before. And this will basically be a topic for the rest, or nearly the rest of the lecture. We'll see how far we get, because we want to show that we have some knowledge of it and the other one is not able to learn it. And a very easy way to see that this is working is that we go back to the idea of how RSA works and square roots. So we have two large prime numbers and only the product is publicly known. And what we're using is that if you factor n, of course, it's the same as knowing p and q. And it's also the same as consistently computing square roots, something we had last time, and we also talked in the exercise about this. Now, this is an interesting thing now. Why? Because if you have a number y, you can compute y squared modulo n. That's very easy. So you can create a pair y squared. But if you have a number, let's call the z, and you want to, and the question is, what is the square root of z? So, just sloppy notation. And this is hard. So for some numbers, and you can choose these numbers, the square roots, but if I give you a number, you cannot compute the square root, because if you can compute the square root, you can factorize n, like a balance. So the question is, how can I prove that I know the square root? Well, the easiest way is I just give it to you. But then you know that I know. But I want to show you that I know it without giving you the square root, because I might be using it for something else. Yeah. So in this context, y squared is somehow a commitment where they say, okay, this is a number for which I know the square root, and y is somehow the basic. And this gives us a first protocol how to show that you know the square root without showing it. Okay, so now I changed notation a little bit because I like to have x as a secret. Okay, so now y is the square number, and I publish only y. So I say this is the square number, and publish to the verifier. So this is y. Now, in order to make this secure, I can say send x again, but I just don't want to. So what I do is, as a prover, I choose a random r and compute another square number, which is a, and just send this a to the other side. So y is a square number, a is a square number. And now something strange happens. So the verifier, who wants to know whether we know this good or not, sends e. And e is just a bit telling what to do as the next thing. Now, if e is equal to 0, then we send r. Yeah, so we send r. What does it tell to the verifier? Okay. Well, r is equal to r squared. So what does the verifier learn if I send e, r? So, I have a secret, and I send it to you. And now to prove something, what I do is I give you basically r squared And if you ask me for it, I give you the square root. So r and r squared doesn't have anything to do with y. So there's no knowledge flowing here. So if just I can send r and r squared, it's not even that I have to send it. Verify could do it as well. Verify could produce r and r squared and just pretend that the prover exists here. So there's no information flying here. Okay. So what happens if in the other case, I'll just move that here. In the other case, if e is equal to 1, we send r times x. Okay. And the verifier checks whether r times x squared is equal to r times y. Okay, what does this mean for the verifier? The verifier now says, okay, that he knows a random number r times x squared is equal to y times a. But, can he produce this without knowing it? Well, he only knows the root of a times y. Now, the verifier could produce this knowledge in the following way, that I could say, I just give this a different name. Let's call this a set. Okay. So we have set. So if I have set squared, and now I want to produce an r squared. So if I take set squared and divide this by y, I get r squared x squared divided by r squared. So I get basically, this is y, sorry, this is x squared. So basically I get r squared, so I get a. So that means that if I give an s, I can compute a. So if I could choose a random number here, set, and compute a, and I still can do this information. So I can, if I know that e is equal to 1, I can produce an a in such a way that r times x, this is the product, fits to it. So that means the verifier doesn't learn here anything else. So in both cases, the verifier doesn't learn anything. However, he learns something that the prover is able to produce with. So the prover is able to produce a square root of r and a square root of r times x. And this is equivalent that the prover must know the square root. And this was the first approach to this idea. So we will repeat this next time and look into this idea because this gives us already a first version of a sigma proof. And it's called a sigma proof because it has this strange interaction which looks like that. So that's the sigma proof. So, and the second thing is that one has to really understand that the prover cannot fake its knowledge. The prover has to know its knowledge, and the verifier can check the knowledge. However, on the communication channel, there is no information flow. So any observer could look into this communication channel and gets no knowledge, and we can prove this by just that the observer just could make this communication on its own. So also the verifier could make this communication. And this is a new level of communication or communication protocols, because you can prove that you know maybe a square root or something else, and the verifier and can prove it to the other person, and he can prove that there is no information flowing to the verifier except the fact that you know this information. And this is the area of zero knowledge proofs. The zero knowledge doesn't mean that you don't know anything, but that you cannot learn anything from that. And yeah, this is complicated. So we do that when we look into what we can prove with a zero knowledge proof. Spoiler alert, everything. You can prove everything with zero knowledge proofs. And then later on, we look in how to make these very complicated proofs faster. Okay, but that's for today. So thank you for your attention and see you on Thursday in the exercise.